All right, let's have a quick look at this HSC question here. When I'm reading this, there's a lot of information, so we just want to try and break it down and see what we're trying to answer. So this is from the 2010 paper, and it's question 8. Assume that the population P of cane toads in Australia has been growing at a rate proportional to P. That is, Cp dt is equal to Kp, where K is a positive constant. First of all, when I'm reading that, I'm already thinking, okay, if I know that the rate is proportional to the amount of things that there are, that's related to exponential growth. Because we know we're talking about growing here, right? So exponential growth, that's already the thought process I'm going through. What information do I have? Well, I know that there are 102 cane toads brought into Australia from Hawaii in 1935, and then 75 years later, in 2010, it's estimated that there are 200 million cane toads in Australia. So this question is asking me, from that information, can you find, if it continues to grow at that rate, can you find how many cane toads there'll be in 2035? And with these exponential growth questions, this one in particular threw a lot of students off because usually they break it down into parts to help you scaffold the question, but they don't always do that. And this one is a bit trickier. Right? How would I approach this? Well, the first thing that I'm thinking is that I know that since I have the PTT equals to Kp, that tells me that the rate is proportional to how many cane toads there are. What they haven't told you is what's the equation that represents how many cane toads there are. And we can assume, because we know that this is the growth rate, I know that P, the population of the cane toads at any point in time, is actually equal to AE to the KT, where A, that's the initial amount of cane toads. So obviously in this case, when t equals to 0, right, it's very clear that, well, you know that there are 102 cane toads, so A times e to the power 0, well, that's just going away, that's just going to be 1, so A is equal to 102. So that's the first thing I know. I know that this is my equation for any kind of general exponential growth model, and I know that my A value is the initial amount of whatever I'm looking at, in this case cane toads, so that's 102, right? So what I'm going to do now is try to think about what information is here. So I know that when t equals to 0, the population amount, that's 102. Now, 75 years later, so when t equals to 75, how many cane toads are there? Well, there's 200 million. Now, when I was reading through the markers comments, one thing that apparently caught students off guard a lot was writing 200 million as a numerical digit, right? So if I'm looking at 200 million, that's the number 200, and millions have 6 zeros, so I'm going to write 6 zeros after that. And the question is, when the population continues to grow, how many cane toads will there be in 2035? Have a think about what value that means for t. Another mistake that caught a lot of students off guard is they saw 2010 and they saw 2035 and they immediately thought, oh, easy, 25 years, right? Without realizing that actually where are you starting from? Well, you're starting from 1935. So how many years later is that? Well, 2035 is just 100 years later. What we're trying to find is what is P going to be at that time, right? How can I go about this? Well, at the heart of any exponential growth question is really looking at this model. And I already know what A is equal to, and T I can substitute based on what time I'm looking at. But the real thing I want to try and find is K. How can I do that? We go to this one here, because here we have the complete picture. I know after how long, how many cane toads there are. I'm going to substitute those values in, right? So I'm going to say, for this one here, let's make an equation to represent this. I know that P is equal to AE to the KT, where in this case, P is 200 million. A is my starting value, or 102. T is going to be 75. And what I'm trying to do is solve for K. I'm trying to see what this growth constant is. Right? So let's keep rearranging here. So this would just be 200 million divided by 102. And this would be e to the 75. When you have an unknown in that exponent, what you really want to do is take the logs of both sides. Okay? In this case, I want to take log with base e, because that's going to help me simplify that better. So 200 million over 102 equals to ln of e to the 75k. And at this point, you can use your log laws just to simplify. And I realized that I can drop that exponent down, and then the ln of e, that's just going to divide through. So the ln of e, that's just going to simplify to just 1. And then all we need to do is divide through by 75. So that would be k is equal to ln of 200 million over 102. Now, I could put 75 all on the denominator there, but to make it easy to enter in my calculator, I'll just multiply it by 1 on 75. So there's my k value. But don't forget, what's the question actually asking, right? It's asking me, after 100 years, how many k-integers are there going to be? Well, now that I've got my growth constant k, I can go back to my model and then substitute the values I know in. So I know that p is equal to 102 times e to the power 100 times k. And again, I suggest that you leave k in this form here. Don't go rounding before you've actually substituted it in. And to save time as well, I haven't written that whole thing into there. I'm just going to substitute in k at this point here in its exact form. When you put that in, you should get this number here. And at this point, again, you could say that that's just approximately 2.5 times 10 to the 10. But I would still write out everything that's in your calculator display. 2.5 times 10 to the power 10. That's how many k-integers there are, which is, I believe, around 25 billion. That is a lot of k-integers. Wouldn't want to be in Australia in 2035 if that's the case. So that's how you can go about and solve one of these exponential questions. We started off not really having anything scaffolded and a whole heap of information. All we really want to do is try and break it down to our exponential model, solve for k, and then use the information we're given to find how many k-integers there'd be after that much time.